Picture a classroom. Just 23 people. What are the odds that 2 of them share a birthday? Most people guess something tiny. The real answer is over 50%. That's the birthday paradox, and cryptographers quietly rely on it every single day. Here's why our gut gets it wrong. Your brain secretly rephrases the question as, does someone share my birthday? And with 22 other people and 365 days, that sounds like maybe a 6% chance. But we're not asking about you. We're asking if any 2 people in the room match. Here's the key. With 23 people, how many pairs are there? Each person pairs with 22 others, but pair AB is the same as pair BA. So we divide by 2. 23 times 22 over 2 equals 253. 253 pairs. That's 253 separate chances for a match. Suddenly 23 doesn't feel so small. Let's make it exact. Instead of computing a match directly, compute the opposite. The probability that everyone is different. Person 1 picks any day. Person 2 must avoid it. 364 out of 365. Person 3, 363 out of 365. Keep going for 23 people. Multiply them together. You get about 49%. So the chance of at least one match is 1 minus that, just over 50%. This is where cryptographers care. Forget birthdays, think hash functions. If a hash has n possible outputs, how many random inputs before 2 of them collide? Not n, about the square root of n. Same pair counting math. That's the birthday attack. It's why a 64-bit hash only has 32 bits of real collision security. And why SHA-256 gives you 128. Your turn. A hash function has 1 million possible outputs. Roughly how many random inputs before there's a 50-50 chance of a collision? It's about 1,000. The square root of 1,000,000. Not 500,000. The birthday rule. To get a 50-50 collision, you need roughly the square root of the space. That's the whole paradox. Count pairs, not people. When collisions can happen between any 2 things, the numbers catch up fast. Intuition says linear. Reality is square root.